In every rear-wheel drive combustion engine vehicle, we find the following parts: the engine, clutch, transmission, drive shaft, differential, axle, and wheels. Front-wheel drive and four-wheel drive vehicles are slightly different, but they all require a transmission. The engine combusts fuel, which moves the pistons and crankshaft, creating rotation. The clutch engages or disengages the engine's rotational energy to the transmission. The transmission contains a number of gears, which transfer the power of the engine towards the wheels and enables us to change the speed and the torque of the vehicle. The shaft transfers the power to the rear differential. The rear differential distributes this power to the wheels, causing them to rotate and propel the car along. Manual transmission requires the driver to know exactly when to change gear, which gear to change to, and also operate the clutch pedal to disengage and then re-engage the engine. We can also get automatic transmission vehicles, which will automatically do all of this for us. The driver simply needs to put the vehicle into drive, and the car will take care. First of all, we have the main housing. This will protect all the internal components and hold them in place. Looking inside, we have the input shaft, the output shaft, and a counter shaft. A number of gears are fixed to the counter shaft. These will therefore all rotate together. On the input shaft, we also have a gear which is in constant mesh with the counter shaft. The gear teeth are at an angle, which is known as a helical cut. These gear teeth gradually engage on multiple teeth, from one side to the other. This distributes the stress on the gears and makes the gear mesh much quieter than a straight cut spur gear. At the other end of the input shaft is the clutch. This will connect to the engine and force the input shaft to rotate. Anytime the clutch is engaged with the engine, it causes the input and counter shaft to rotate. There are also a number of different size gears on the output shaft. These are also in constant mesh with the gears on the counter shaft, and so when the counter shaft rotates, so will the output gears. However, notice that the output shaft does not rotate with the output gears. That's because each output gear sits on a needle bearing. This allows the gear to rotate independently from the shaft. If we look at the output shaft, we see there are a number of spline sections. These are grooves which are cut into the metal. A synchronizer hub fits over the splines. The splines will lock the hub in place so that it will rotate with the shaft. Another component called the synchronizer sleeve will fit over the hub. The outer surface of the hub and the inner surface of the sleeve are both splined. This interlocks the two components. The sleeve can move forwards and backwards on the hub. When the output shaft rotates, so will the hub and the sleeve, but not the output gears. Attached to the channel, on the outside of each of the sleeves, is a shift fork and a shift rod. The rod connects to the gear shifter. The gear shifter moves the rod backwards and forwards, which therefore also moves the fork and sleeve backwards and forwards. On each of the output gears, we find some additional straight cut teeth. These teeth will align with the spline teeth inside the sleeve. When the gear is selected, the teeth inside the sleeve align and interlock with the straight cut teeth on the gear. The gear will now be interlocked with the sleeve and the output shaft. So, when the input shaft rotates, this rotates the counter shaft, which rotates the output gear, and this now rotates the output shaft. When the gear is disengaged, the sleeve returns to its default position, allowing the output gear and the sleeve to rotate independently from each other. The problem we face is that the output shaft and the sleeve are rotating at different speeds to the output gear. So, when we engage the sleeve, the teeth are going to collide and grind. To overcome